frequency band besides high frequency and the mid band GAN. That's the low frequency band where the coupling capacitors and the bypass capacitors are effective in determining the gain of the overall amplifier. So to determine the low frequency gain or the transfer function of the common source amplifier, this is shown in figure below. The circuit has the DC sources eliminated, so you see that the current source I is open and the voltage source at the drain is short circuited. So at drain you have the short circuit over here, VDD is 0, and ID has been made to be open over here because ID was biasing this common source configuration in saturation region, so we don't have this the source at the current source at the source terminal of the transistor. Okay, so you see we can do a straightforward analysis starting from the input of the transistor at the gate. So but one thing more to notice first is that we are not considering any output resistance, small signal output resistance of the MOSFET, that is R0 is also taken to be infinitely large, so it is no concept. So the in the common source configuration, the small signal resistance between the drain and source is infinitely large, so it's open circuited. Okay, and the MOSFET itself is being modeled by at source the resistance of the MOSFET is 1/GM, okay, in ohms. So there is a analysis done in section 4.12 of the course text if you want to have a look. R0 does not much affects the overall transfer function and the gain as a function of frequency, and in the low frequency regions. The output voltage is also not much affected by R0. Okay, so you can have a look at the SPICE analysis done in 4.12. So we should perform the small signal analysis directly on this circuit. However, we'll ignore R0 in this discussion. So this is done in order to keep the analysis simple, and we shall thus focus our attention on the significant issues over here. So now the analysis begins at the signal generator over here by finding the fraction of V signal that appears at the transistor gate or the input of the transistor. So this is the gate terminal over here. Okay, and you can see that we are not shorting out this coupling capacitor CC1, which is coupling the AC signal at the gate. So what we can do is, well, to find the fraction of the input signal that appears at the input of the transistor, we can use the voltage divider rule. Okay, because of the resistance RG and a linear combination of the impedance resulting from R signal and the resistance of R signal and the capacitive reactance of the coupling capacitor. So it can be written as RG over RG plus R signal plus 1 over SCC1. Okay, so where S is your complex frequency variable, you can find the frequency response. You can substitute this by J omega. So this is the fraction, okay, of the signal that input signal that is appearing at the gate of the MOSFET. Okay, and you can already see the dependence of the available input signal in terms of frequency as okay. Now this expression can be rewritten in an alternate form. The motivation of writing it in this form is that, well, you see that this transfer function is a single pole high pass type response. Okay, I mean this up until this section, the input section of the MOSFET is a single pole high pass filter of the form. Let's say there is a capacitance, okay, and then there is the dominant is the capacitive reactance, which is dominating over here, and then you have a resistance, okay, and the overall transfer function in terms of those elements for such a circuit, single pole circuit, is of the form Ks divided by S plus call it omega naught, where omega naught is the 3 dB frequency, okay, or the corner frequency, and the inverse of omega naught is the time constant of the circuit. So it's a single pole high pass type circuit. Okay, so it's very easy to see the break frequency or the corner frequency, that is in terms of the coupling capacitor and the resistances at the input and the gate of the MOSFET. So Uh, this 3 dB frequency is 1 over CC1 RG plus R signal. Okay, and you can see the frequency dependence occurs at the input of the or at the gate of the MOSFET. So that's the fraction. So Vg is the fraction of V signal that is available at the gate of the MOSFET. So we see that the expression for the signal transmission from the signal generator to the amplifier input has acquired a frequency dependent factor. Okay, so there is a frequency dependence in this expression you see. So we do recognize that this factor as a function of frequency, it's a function of actually a single pole network of the high pass type with a break or the corner frequency of 1 over CC1 RG plus R signal. Okay, so over here you can see CC1 is the coupling capacitor, RG is the resistance at the gate, and R signal is the output source resistance. So in terms of those external circuit parameters, we have the break frequency or the 3 dB frequency, which just appears in the transfer function at the which is relating the signal input signal source and the voltage available at the gate of the MOSFET. Okay, so the effect of the coupling capacitor CC1 is to introduce a high pass response with the break frequency that we should denote by omega p1. So omega p1 is basically the same as omega naught CC1 RG plus R signal, inverse of that. And you can say that the time constant is inverse of that, is 1 over tau. Okay, that's 1 over tau. So continuing with the analysis, we next determine the drain current, ID by dividing the gate voltage Vg by the total impedance in the source circuit, which is the summation of the gate resistance 1 over Gm transconductance gain, and then the capacitive reactance, that is the bypass capacitor Cs. So you see this linear combination is formed here, and this transistor, this MOSFET is this NMOS MOSFET is having the resistance of 1 over Gm at the source, and then there is at source there is a bypass capacitor as well, Cs. So 1 over Gm plus 1 over SCS is going to give you the impedance at the source terminal. Okay, this is the source terminal. So Vg divided by the impedance at source is going to give you the current ID in the source branch. So ID is written as Vg over then you have the linear combination of the source resistance 1 over Gm and the bypass capacitive reactance. So this expression can also be and we rewritten in the form of a high pass type, single pole high pass type. Why it is single pole? Because we only have one corner or break frequency and one S plus omega naught factor. If you would have another, let's say S plus omega 2 or S plus omega 3, so on and so forth, then it would have been 2 pole, 3 pole, or multi-pole high pass type response. But this is a single pole high pass response, high pass type response. And the corner frequency again can be seen that is introduced by the coupling capacitor Cs. So we observe that Cs introduces a frequency dependent factor, which is also of the high pass type. Thus the amplifier requires another break frequency omega p2, which is this factor Gm over Cs. Okay, so I mean again this has a transfer function of the type Ks over S plus, call it omega p2. Okay, because p1 was for the work between the signal generator and the input of the transistor. Over here you have you're evaluating the transfer function at the source. Okay, so we have two break frequencies basically. We have omega p1 and then we have omega p2. Omega p2 is due to the bypass capacitor Cs. Okay, and omega p1 is due to the coupling capacitor CC1. So you see each capacitor is introducing a frequency dependent transfer function of its own, and then it's also introducing the corresponding pole or the break frequency. So if you continue our analysis, if you're going to find, for example, the output current or the output voltage, then we have another coupling capacitor CC2 which is going to introduce another pole, a third pole because of CC2, the coupling capacitor. So to complete analysis, we find the output voltage by first using the current divider rule to determine the fraction ID that flows through RL. So over here you see, well, you have the capacitive reactance 1 over omega CC2, okay, then plus RD plus RL for the output branch at the drain. So if you apply the current divider rule to find I naught, okay, to find I naught, then the expression can be written as such. So this is RD over RD plus 1 over SCC2, which is the coupling capacitor reactance, plus RL. Okay, so if you multiply this expression with RL, which is the load over here, then you can find what is V naught. Okay, so you'll have a frequency dependent output signal V naught in terms of the complex frequency variable S. Okay, which you can see over here and here. So again, this is the high pass type response. Okay, V naught is I naught multiplied by RL. The whole expression can be written as such. Okay, and you can see from this that your third break frequency omega P3 is 1 over CC2 RD plus RL. Okay, so each capacitor is introducing its own break frequency. So these break frequencies, whichever is higher, is going to determine the 3 dB frequency or FL of the overall common source amplifier. So from this expression, CC2 introduces a third high pass factor, given amplifier a third break frequency over here, which is again it's of the same form as that you've seen earlier for omega P1. Okay, when we were considering the input gate voltage for the MOSFET. So a very similar expression comes out for the second coupling capacitor at the output. So this is in the form, this is in the same form. So but this break frequency is due to the coupling capacitor CC2. So if you combine to have a complete transfer function of the CS amplifier, combining all these three, combining the effect of all the frequency dependencies of all the three capacitances in one transfer function, then you have to relate the output signal to the input signal. So we can combine all three transfer functions. For example, this transfer function consists of the input V signal. Okay, then the second transfer function is in terms of the current ID. Okay, so we're going to use this transfer function for ID current is over here. You see, we use ID to determine the output current from the current divider rule. So basically, you can use this transfer function, and then you can substitute this ID over here. Okay, this is going to bring VG over here. That's the gate voltage, and that gate voltage, if you recall, in the first transfer function was expressed as a fraction of the signal generator voltage. Okay, that is available. So then you can substitute for VG over here, and this will result in the relation of V naught with V signal. Okay, so then V naught by V signal, if you combine them, will be of the form minus RG over RG plus R signal, and you can see there is a parallel term overcoming RT parallel RL. You can see this factor is RD parallel RL. GM is going to come from here. Okay, and then you are going to have those three basically these factors, these break frequency or the corner frequency factors in all three transfer functions combined together, all high pass type. So you can see we'll have omega P1, we have omega P2, we have omega P3s. Okay, so it's a threefold transfer function. So the overall low frequency transfer function of the amplifier can be found by combining all the transfer functions and replacing the break frequencies by their symbols in them. Okay, so it can be written as such. This is the transfer function relating the output to the input. So this is in terms of the complex frequency variable S. So the low frequency magnitude response can be obtained from the above equation by replacing S by j omega and then evaluating the magnitude. Okay, so in many cases, however, one of the three break frequencies can be much higher than the two, say by a factor of 4. So in such case, it is the highest frequency, highest break frequency, that's going to provide the lower 3 dB FL, and we do not have to do any additional hand analysis. So for instance, if omega P2, I mean usually, okay, you see the difference in omega P1, P3 is, so omega P1 is in terms of the coupling capacitor CC1, which is of the order of some microfarads, 100 microfarads. Then RG is usually larger than R signal in practice, with the biasing resistors at the gate. So basically this these are the dimension of these external circuit parameters. But the difference between omega, this is omega P1, okay, this is omega P1, then this is omega P2, and The difference of omega P2 with regards to omega P1 and P3 is that it consists of the transconductance parameter Gm. Okay, and omega P2 is usually larger than omega P1 and P3. So this omega P2 is basically, this is going to imply that omega FP2 is going to set your 3 dB frequency of the MOSFET low frequency response. Okay, because omega P3 again is going to have the same, almost the same corner frequency. CC2 is also in some 100 microfarads range. RDRL in few kilo ohms. So this is going to have the same effect. Okay. So since omega P2 is larger, then FL will be FP2. Okay, which means in this case bypass capacitor determines the low end of the midband. That's it.